Nanofluidics is the study of the behavior, manipulation, and control of fluids that are confined to structures of nanometer characteristic dimensions. Nanofluidics have had a significant impact in biotechnology, medicine, and clinical diagnostics with the development of lab-on-a-chip devices for PCR and related techniques. That's the nano world, a place where a hair strand seems like a gigantic mountain and water behaves more like honey. Historically, nanofluidics emerged from the need to understand and control the unique behaviors of fluids at this incredibly small scale. From the first observations of nanoscale phenomena in the 1980s to the development of sophisticated nanofluidic devices today, the field has evolved leaps and bounds. But why is nanofluidics important? Well, it's all about control. By understanding the unique properties of fluids at the nanoscale, we can create devices and systems that perform tasks with unprecedented efficiency and precision. From targeted drug delivery systems that can navigate the human body to advanced water purification technologies that could revolutionize access to clean water, the applications of nanofluidics are wide-ranging and transformative. And at the heart of nanofluidics lie some basic principles of fluid mechanics. These principles, however, take on new meaning at the nanoscale. Think about surface tension, for example. At our scale, it's what allows water striders to skate on a pond's surface. But, at the nanoscale, surface tension becomes a dominant force, capable of driving fluid flow in tiny channels and shaping droplets into perfect spheres. So there you have it. Nanofluidics may deal with the extremely small, but its implications are huge. As we continue to explore this field, we are unraveling the mysteries of the nano world and using them to solve real-world problems. Nanofluidics, although minute, is proving to be a giant in the scientific world. Fluid dynamics, a concept familiar to many, but let's examine it under a microscope. Now, we're not talking about merely shrinking the scale. We're venturing into the realm of nanoscale fluid dynamics, where the rules of the game are rewritten. At this scale, the behavior of fluids diverges significantly from what we observe in the macro world. For starters, the continuum hypothesis, which assumes that fluids are continuous masses rather than collections of discrete molecules, starts to wobble. It's still applicable, but with some caveats, as the distinctness of individual molecules becomes more pronounced. Then there's the matter of surface forces and interface science. At the nanoscale, surface forces, which are often overlooked in macroscale fluid dynamics, come into the limelight. These forces, resulting from intermolecular interactions, can profoundly influence the flow and behavior of fluids. Lastly, let's touch on electrokinetic phenomena. In nanofluidic systems, surface charges on the walls of the nanochannels can induce a flow in response to an applied electric field, a phenomenon known as electroosmosis. This adds another layer of complexity to our understanding of fluid dynamics at the nanoscale. As you can see, the world of fluid dynamics takes a fascinating twist when we shrink things down. Now that we understand the mechanics, let's talk about how we make these tiny systems. To start, it's important to note that the choice of materials for constructing nanofluidic systems is crucial. The material needs to be compatible with the fluid it will interact with, and it should be durable enough to withstand the forces at the nanoscale. Some common materials used include silicon, glass, and polymers. Each of these has its own unique set of properties that can be leveraged to optimize the behavior of nanofluidic systems. Once we've chosen the right material, we can begin the process of fabrication. There are several techniques available, but one of the most common is lithography. This is a process where a pattern is transferred onto the material using light or electrons. The pattern can then be etched into the material, creating the intricate channels and structures needed for nanofluidic devices. But the fabrication process doesn't end there. Surface modification techniques are often employed to further control the behavior of fluids at the nanoscale. This could involve changing the surface charge or modifying the hydrophobicity or hydrophilicity of the material. These modifications can have a profound effect on how liquids move and interact within the device, giving us even more control over the system. Despite these techniques, the fabrication of nanofluidic devices is not without its challenges. Working at the nanoscale means dealing with forces and phenomena that don't come into play in larger systems. For example, the surface forces become dominant over volume forces, leading to unexpected fluid behavior. Additionally, the fabrication process itself can be complex and time-consuming, with a high degree of precision required. Yet these challenges are part of what makes nanofluidics so exciting. They push us to think creatively, to come up with novel solutions and techniques, And when we do overcome these hurdles, the rewards can be immense. From lab-on-a-chip devices that can perform complex analyses on a single droplet of fluid, to nanoscale pumps and valves that can precisely control fluid movement, the possibilities are virtually endless. The crafting of this nano world, while complex, opens up a universe of possibilities. From theory to practice, let's explore how nanofluidics is making waves in various industries. This fascinating world of nanofluidics is not just about theories and principles, it's about creating tangible, functional devices that can transform the way we live, work, and research. At the heart of nanofluidics are devices engineered to manipulate fluids at the nanoscale. These nanofluidic devices are designed based on the unique operational principles of fluid mechanics at the nanoscale. Imagine a world so small where the conventional rules of fluid dynamics are bent and reshaped, leading to intriguing and unexpected phenomena. One of the key applications of nanofluidics is in the creation of molecular sieves and filters. These devices are not your everyday filters. They operate at the molecular level, enabling the precise separation and analysis of complex mixtures. They leverage the unique properties of fluids at the nanoscale to isolate and identify individual molecules, opening doors to new possibilities in drug discovery, disease detection, and environmental monitoring. Then, we have nanofluidic transistors and circuits, where the worlds of fluidics and electronics merge. Just as electronic transistors control the flow of electrons, nanofluidic transistors control the flow of ions. These devices harness the charge-carrying ability of ions to create circuits that can function in wet environments, making them ideal for use in biological systems and advanced sensors. Lastly, let's delve into the realm of lab-on-a-chip devices. Imagine shrinking an entire laboratory onto a single chip. These devices take advantage of nanofluidics to perform complex biochemical reactions in microscale channels, drastically reducing the time, cost, and resources needed for analysis. From separating molecules to controlling ions and miniaturizing labs, nanofluidics is revolutionizing our approach to solving complex problems. The applications of nanofluidics are as diverse as they are revolutionary. Behind every practical application, there's a foundation of theory and computation. This statement holds true in nanofluidics as well. Diving into the theoretical aspect, models for describing fluid flow at the nanoscale become crucial. These models take into consideration the unique characteristics of nanoscale fluids, such as the interplay of surface forces, quantum effects, and the dominance of Brownian motion. They help us understand the behavior of fluids in confined geometries and contribute to the design of efficient nanofluidic devices. Equally important are computational approaches. Computational fluid dynamics, or CFD, has become an essential tool in nanofluidics research. It provides a numerical method for solving and analyzing problems that involve fluid flows, allowing researchers to predict and visualize how fluids will behave under various conditions. Molecular dynamics simulations offer another powerful tool. These simulations provide an atomistic perspective, enabling us to study fluid interactions at a molecular level. They can capture the intricate dance of molecules, revealing the fundamental mechanisms of nanoscale fluid behavior. However, modeling and simulation of nanofluidic systems are not without challenges. The complex interplay of forces at the nanoscale, the need for high computational resources, and the difficulty in validating models experimentally all add layers of complexity. But it's these challenges that drive researchers to innovate, pushing the boundaries of what's known and what's possible. These theoretical and computational approaches are the backbone of nanofluidics research. From heat transfer to mass transport, let's examine how things move in the nano world. To understand nanofluidics, we need to delve into the transport phenomena that occur at this minute scale. You see, the rules here are a bit different from what we're used to in our macro world. Consider heat transfer mechanisms. In nanofluidics, heat transfer isn't just a simple case of hot moving to cold. At the nanoscale, we have to consider a host of factors, such as the thermal conductivity of the fluid, the interface between the fluid and the channel walls, and even the velocity of the fluid flow. These factors can significantly alter heat transfer rates, leading to fascinating and sometimes counterintuitive results. Next, let's talk about mass transport and molecular diffusion. In the nanofluidic realm, molecules don't move around randomly as they do in our macro world. Instead, they're influenced by quantum effects and surface forces, which can cause them to move in unexpected ways. This can lead to highly efficient transport processes, with molecules moving rapidly and directly to their destination. Electroosmotic flow and electrophoresis are two more intriguing phenomena that occur in nanochannels. When we apply an electric field across a nanochannel, the fluid can move in response, a phenomenon known as electroosmotic flow. Conversely, electrophoresis refers to the movement of charged particles under the influence of an electric field, which can be leveraged for tasks like separating molecules of different sizes. Finally, let's touch on capillary effects at the nanoscale. You've probably seen water climb up a thin tube or a plant stem. That's capillarity at work. But in nanofluidic channels, these capillary effects can be dramatically amplified, giving rise to superhydrophobic or superhydrophilic surfaces. These transport phenomena demonstrate the unique behaviors of fluids at the nanoscale. They underscore the fascinating world of nanofluidics, where we're still uncovering new phenomena and learning how to harness them for technological advances. Nanofluidics is not just about movement, it's also about detection and analysis. In the world of nanofluidics, we're not only concerned with the manipulation and control of fluids at the nanoscale. We're also heavily invested in using these tiny systems as platforms for detecting and analyzing biomolecules. These platforms can be thought of as miniature laboratories where we can observe and study biological interactions on an incredibly small scale. Imagine being able to scrutinize the behavior of a single molecule in real time, witnessing its interactions, movements, and transformations. Single molecule sensing techniques allow us to do just that. By reducing the scale to such an extent, we can gain insights into molecular dynamics that would be impossible to observe in larger, more complex systems. But how do we actually see what's happening at the nanoscale? This is where the integration of nanofluidics with optical and electronic detection methods comes in. Through the use of advanced optics, we can monitor the behavior of individual molecules as they move through nanofluidic channels. Electronic detection methods add another layer of sophistication to our nanofluidic toolset. These techniques leverage the unique electrical properties of nanoscale systems to detect and analyze biomolecules. For instance, by applying a voltage across a nanofluidic channel, we can measure the electrical resistance of the fluid. This can provide information about the number and type of molecules present, giving us a powerful method for analysis. But it doesn't stop there. The integration of optical and electronic detection methods with nanofluidics opens up a whole new world of possibilities. We can now begin to examine biological processes at the molecular level, shedding light on the fundamental mechanisms that drive life itself. As we continue to delve deeper into the world of nanofluidics, we're constantly discovering new ways to exploit these tiny systems for scientific discovery. The ability to detect and analyze single molecules in real time is just one example of the incredible potential of nanofluidics. With nanofluidics, we can detect and analyze particles with unprecedented precision. From energy storage to water purification, nanofluidics is shaping our future. Imagine a world where energy storage systems are so efficient that power shortages become a thing of the past. This is not a distant dream, but a tangible future made possible by nanofluidics. By manipulating fluids at the nanoscale, we can enhance the performance of batteries and fuel cells. Nanofluidic channels, with their unique ion transport properties, can be leveraged to create high-capacity, fast-charging energy storage systems. Let's take a leap from land to water. Freshwater scarcity is a pressing global issue, but nanofluidics may hold the solution. By developing nanofluidic filters, we can desalinate seawater more effectively and at a lower cost than conventional methods. These filters, fine-tuned to the molecular scale, can selectively remove salt ions, yielding fresh water from the oceans that cover over 2/3 of our planet. But the power of nanofluidics doesn't stop there. It extends to the very materials that make up our world. By controlling fluid behavior at the nanoscale, we can guide the self-assembly of nanoparticles into advanced materials with tailored properties. These materials could revolutionize fields as diverse as electronics, medicine, and aerospace, opening up new horizons of possibility. As we look to the future, we see a world in which nanofluidics plays a pivotal role. It's a world where efficient energy storage reduces our reliance on fossil fuels, mitigating climate change. It's a world where access to clean water is not a privilege, but a right. It's a world where advanced materials enable technologies we can barely imagine today. But this future is not preordained. It requires continued research, exploration, and innovation in the field of nanofluidics. It requires the brilliant minds of scientists and engineers pushing the boundaries of what's possible. It requires us to embrace the power of the small to make big changes. The future of nanofluidics is bright, and its potential to revolutionize our world is immense.